Large Hadron Collider infrastructure talk. You probably know the Large Hadron Collider over at CERN. We heard quite a bit of it in the recent talks. This time we will have a deep dive into the infrastructure. You can assume over the next speakers are doing a great job. Basically, it's pretty obvious because we're not stuck into a giant supermassive black hole. So please welcome, with a very warm applause, Severin and Stefan.
Thanks. Related. Yeah, hello everyone. Thanks for coming. So many people here, quite nice. In the last couple of years, we had several talks about, basically the physics perspective of LHC. How physicists analyze data at LHC, how physicists store all the data, etc. And we would like to give more an engineering perspective of the whole LHC. So 3 years ago, we had a talk by Axel about how physicists analyze massive big data. And then last year, we had a talk conquering large numbers at LHC by Carsten and Stephanie. And we would, as I mentioned already, we would like to give more an engineering perspective. We are Stefan and Severin. We are both electrical engineers working at CERN. Stefan is working in the experimental physics microelectronics section. And he will give a second talk tomorrow about designing high reliability digital electronics together with Shimon tomorrow morning at 11:30. And I'm, as I mentioned already, also working at CERN. I'm working in the electronics for machine protection section. I will describe briefly later. A short disclaimer, the LHC is a pretty big machine, and we try to explain it as good as possible. 45 minutes is not really enough to talk about everything, because I think you can basically take one of the topics we are talking here about now and talk for 45 minutes only about one specific topic. But we try to give an overview as good as possible. So imagine you want to build an accelerator in your backyard. Okay, maybe not in your backyard because LHC is quite big, so 27 kilometers in diameter is quite big. But basically, we figured out three main challenges you have to take. First of all, we have to accelerate particles because otherwise it's not a particle accelerator. Second, we have to keep the particles on a circular trajectory. And then third, we have to make sure that the particles which are inside our beam tube or beam pipe don't collide with anything which is there. For example, the beam pipe itself, air molecules, etc. And the solution we adopted for LHC there is that we accelerate the particles with high power radio frequency cavities. Then we have a beam control system which is quite sophisticated using superconducting magnets. And then we have the beam pipe itself, which is evacuated, so it's under vacuum conditions to avoid any collisions we have inside with gas molecules, etc. A brief overview about the location itself. So probably many of you know already that CERN is next to Geneva. So it's in the western southern part of Switzerland. When we zoom in a little bit more, then we have here an artificial picture of LHC itself in the red circle there. To put it a little bit in a perspective, we have a relatively big airport there. You can see there it's a 2,200 meter long runway. We have Geneva Lake next to it, and that's only one small part of Geneva Lake, but nevertheless. And what is also quite nice, we see Mont Blanc from LHC, from CERN. When we zoom in a little bit more, then we basically have the big circular collider there. That's LHC itself, and we have pre-accelerators. I will talk in a few minutes about. Basically, we have two main campuses. We have the Meran site, which is in Switzerland, and we have the Preuve site, which is in France. Then at LHC itself, we have 8 service points. We also call this just points. To briefly go through all of them, we have point 1, where we have the experiment called Atlas, one of the big and major experiments at LHC. Then at the exactly opposite side of Atlas, we have CMS at point 5. Then we have a little bit smaller experiment, which is Alice. It was basically constructed for lead-ion runs. We will talk about this later. And then we have another relatively small experiment. It's called LHCb, and that's the only non-symmetrical experiment at LHC. These are, I think, the 4 experiments you already maybe heard of. Then there are 4 or 3 other small experiments. We have LHCf at point 1. It's a forward scattering experiment at point 1. So basically they are taking data like scattered particles from Atlas itself. Then we have Totem. It's also a forward scattering experiment at point 5. Then we have, we have Mödal, which is the experiment at point 8. They are looking for magnetic monopoles. Then we have Totem, sorry for that, at point 5. And then we have a relatively new experiment, which is called Phaser. It's actually under construction, and it will be used starting from 2021. And it's a forward scattering experiment, where they try to detect neutrinos. Then we have point 4. There we have the RF cavities to accelerate the particle beam itself. We have the beam dump area. So when there is like a fault in a machine, or we just want to dump the beam, then we use the beam dump system at point 6. And then we have 2 more general service areas. It's point 3 and point 7. LHC would not be possible without the pre-accelerator complex. So we have a relatively big one, and it's also sometimes relatively old. On the left-hand side of the slide, you can see LINAC 2. It's an old linear accelerator, which was used until last year. It's now phased out, and now we have LINAC 4, which is also a linear accelerator, and it has a little bit higher acceleration. Then we have the proton synchrotron booster. It's the first circular collider, so you can see 2 pictures there. What is relatively special about PSP is that we have there 4 beam pipes instead of just 1 beam pipe. Then we have the proton synchrotron accelerator, which is the next stage for acceleration. It then has only one beam pipe, and then we are going from PS, we are going to SPS, which is the super proton synchrotron, which has circumferences of 7 kilometers. There we basically accelerate the particles the last time, and then they're injected in LHC itself. We mentioned a few accelerators already, basically everything which is highlighted here, but CERN is a little bit more. So CERN is famous for LHC, I would say, but there is much more than only LHC. So only around 15% of the protons which are accelerated in a pre-accelerator complex are really going to the LHC itself. So there's much more. There's material science, there's antimatter research, and all different other kinds of research going on. Of course, everything has to be controlled. It's called CCC, the CERN Control Center. It's located at the Bresson site. Looks like that. So basically, we have 4 Cs looking to each other, and there the operators are sitting 24/7 and operate the whole machine. So basically, the whole pre-accelerator complex, all the energy, cryogenics, and LHC itself. Before you ask, everything is running on scientific Linux, so we have basically our own Linux distribution which is used there, and of course it's open source. Talking about the LHC beam itself, we have 2 beams. One is running clockwise and the other one is running anti-clockwise, because we don't have a fixed target experiment where we basically let the accelerated particles colliding with like a fixed target, like metal or something like that. We have controlled collisions at 4 points, we mentioned before. Most of the year we have proton run, so we have protons and protons colliding towards each other. And then we have at the end of the year, nearly starting from November to December, we have a lead-ion run. The proton itself, it's not really like a fixed straight line of particles. We have something called bunches. You can imagine a bunch a little bit like a spaghetti. It's basically the same length of a spaghetti, but it's much thinner than a spaghetti. And each bunch, when you have a proton run, then each bunch consists of approximately 100 billion protons. And when you have lead-ion run, then we have approximately 10 million lead ions in LHC. And last year, we operated with 2,565 bunches in the LHC itself. The LHC tunnel. We already talked about the tunnel itself. It is 27 kilometers long. And you can see maybe a little bit on this graph that we have 8 straight sections and we have 8 arcs in the tunnel. Basically, the straight sections are always there where we have like service cavities or where we have service areas and also the experiments. Because it's not so good visible in this picture, I put a picture here. Basically, that's a straight section of LHC. You can basically just see the beam pipe itself with aluminum foil around it. There are also no magnets. And when we look in the arc section of LHC, then you see here the arc itself. And I think it's quite famous picture of LHC itself because we have this blue dipole magnets there. The tunnel itself is an old tunnel used previously by LEP, the Large Electron Proton Collider. It has a diameter of 3.8 meters, and the circumference is approximately 27 kilometers. Inside the tunnel, we have, first of all, cryogenics. So we have big tubes, stainless steel tubes to carry all the cryogenics, so liquid helium and gaseous helium. Then we have the magnet itself to bend the particles. And then we have electrical installations to carry like signals from the magnets, to have safety systems, electricity, etc., etc. Geography is a little bit complicated in the area because we have, in the western part of LHC, we have the Jura mountain range. And this Jura mountain range has a relatively hard material. It's made out of, not made, but nature. I mean, it's limestone. So it's relatively complicated to dig into this material in comparison to all the other areas at LHC. So when you would basically put a straight section of LHC, then you have to dig much more in the relatively hard limestone. So that's why it was decided that the lab or LHC tunnel is tilted a little bit. So we have a tilt angle of 1.4% there. The depth is approximately between 50 meters at 0.1 or 0.8 up to 170 meters deep at 0.4. We already talked a little bit about magnets, but we would like to go a little bit more into details now. So why do we need magnets? Maybe you learned at school that when you have a magnetic field and you have charged particles, then you can bend particles around an arc in a magnetic field. Depending on the charge of the particles, you bend them around on the right side or the left side. That's this famous right hand and left side rule you maybe learned during school. And at LHC, we cannot use normal magnets like typical magnets. We have to use electromagnets because normal magnets would not be strong enough to build an electromagnetic field which is feasible to bend the particles around the whole tunnel. At LHC, we use in the dipole magnets a magnetic field of 8.3 Tesla, and to do this, we need a current of 11,850 amps. We have basically two different types of magnets. We have bending magnets, so the dipole magnets I mentioned quite often already. And then we have injection and extraction magnets. They are also dipole magnets, but they are a little bit differently constructed because the injection and extraction magnets have to be quite fast because they have to basically be powered up at full, the full magnetic field in several microseconds. Then we have higher order magnets, which are quadrupole magnets, sextupole magnets, and octupole magnets, etc., etc. And they are used for focusing and defocusing the beam itself. In total, we have 1,200 dipole magnets in LHC. We have around 850 quadrupole magnets, and we have 4,800 higher order magnets, but they are normally quite short, so shorter than the other magnets. The dipole magnets consist of two apertures. They're used to bend the beam around, so I already said. In the middle of the magnet itself, we have a cold bore, so there are the particles flying around. Then there's a metallic structure. You can see this in the picture. There's this shiny metallic sphere you see there. And then we have, next to the cold bore, we have the two apertures to bend the particle and build the magnetic field itself. The dipole magnets have a length of 50 meters, and the manufacturing precision is plus minus 1.5 millimeters. Then we have quadrupole magnets. They are used for focusing and defocusing the beam. The problem is that we have bunches where are basically equally charged particles inside. And the Coulomb force tells us that when we have like equally charged particles, then they basically want to fade out from each other, and in the end they would just hit the beam pipe itself, and we could maybe destroy the beam or cannot do any collisions. So what we do is we use quadrupole magnets as similar to lenses, because we can focus and defocus the beam. The quadrupole magnets, the name already suggested it, that we have basically 4 apertures. So we have on the left and the right side 2, and then we have on top and bottom we have also a few of them. To go a little bit into detail about the focusing and defocusing scheme. In the beginning we have a particle beam which is not focused, but we want to focus it. Then we go to the first quadrupole magnet, so we focus the beam. And this is only done in one axis. That's a little bit a problem. So in the second axis, we don't have any focusing. We have a defocusing effect there. And then we have to use a second quadrupole magnet for the other axis, in this case the y-axis, to focus the beam even further. And you can even see this here in the z-axis. That's basically the the cut of the beam itself. You can also see that in the beginning we have on the left side, we have a non-focused beam, and then we focus it in one axis, so we have like a little bit more ellipse, and then we focus in the other direction, then we have a different ellipse. So we have to use several quadrupole magnets in a row to really focus the beam in the way we want to have it. In the LHC magnets, we have quite high currents. We need these currents because otherwise we cannot bend the very high energetic particle beam. And to use normal conducting cable, it would not be possible to basically build a magnet out of it. So what we do is we use materials which are called superconducting materials because they have a very good effect. They go to basically zero resistance at a specific temperature point. And after this point, or when we basically go lower, then we have the current can flow without any losses inside it of it. But to reach the state, we have to cool down the magnets quite heavily, which is not so easy, but it can be done. And on the right side, you basically see a very historic plot that was 1911 in Denmark. A researcher called Heike Onnes detected for the first time a superconducting effect in mercury, and it was detected at 4.19 Kelvin. To show you a little bit the comparison between a normal conducting cable and a superconducting cable is we put a picture here. So that is basically the same amount of cable you need to use to carry 13,000 amps, and to do the same or to transport the same amount of energy, we also can use a very small superconducting cable, and I think it's quite obvious why we use here superconducting cables. At LHC we use niobium tin as material, and this material basically goes into superconducting state as at 10 Kelvin, but to have a safe operation doing LHC, we have to cool it down at 1.9 Kelvin. Superconducting magnets have some benefits, but also some downsides. So sometimes they change their state because there are small vibrations in the magnet, or the temperature is not precise enough, or the current is too high. Then they change that state, and it's called quench. And we basically can detect a quench when we measure the voltage across the magnet, because the resistance changes at this point. So when there's a quench, then the resistance changes quite rapidly in milliseconds, and we can detect this voltage rise with sophisticated electronics. On the right side, you see a board I'm working on. So basically here we have a measuring system to measure the voltages across the magnet, and then we have a detection logic implemented in the FPGA to basically send triggers out and open an interlock loop. Interlock loop is a system at LHC. You can imagine it a little bit like a cable going around the whole tunnel, and there are thousands of switches around this interlock loop. And as soon as one of the detection system basically opens the interlock loop, then basically the whole machine will be switched off. And what means switched off is basically that we will power down the power converter, but then the energy is still in the superconducting magnet, and it has to be taken out of the superconducting magnet. And therefore, we use dump resistors to extract the energy. And here you can see a picture of such a dump resistor. It's quite big. It's in a stainless steel tube, oil-cooled. It's approximately 3 or 4 meters long. And when basically there was a quench and the energy was extracted via these resistors, then the whole resistor is heated up by several hundred degrees, and it needs several hours to cool it down again. Power converters. The power converters are used to power the magnet itself, so they can produce a current of approximately 13,000 amps and a voltage of plus minus 190 volts. And you can see a picture how big it is. One downside with the power converters is that they have to be, not downside, but one difficulty is that they have to be very precise because every instability in the current would have or has a direct effect on the beam stability itself. So basically the beam would be not diverted in the right amount of length. So that's why they have to be very precise and have to have a very precise stability. So here I just pointed out, like in 24 hours, the power converter is only allowed to have a deviation of 5 ppm, and in comparison for 13,000 amps, we have a deviation of 65 milliamps. So the power converters have to be very precise. And to do that, we had to develop our own ADC, because at the time when LHC was built, there was no ADC on the market which was able to have this precision. And also the whole ADC is put into super precise temperature controlled areas, and it is calibrated quite regularly. Okay, cryogenics. We already talked about that we have superconducting magnets, and they have to be cooled down quite low. So the superconducting magnets we have at LHC have to be cooled down to 1.9 Kelvin. And we are doing this when we start the LHC. Then we cool down in the first hand with liquid nitrogen. So approximately 6,000 tons of liquid nitrogen are put through the magnets to cool them down to 18 Kelvin. And afterwards we cool the magnets down with liquid helium. And the liquid helium is at 1.9 or 1.8 Kelvin. And to put it a little bit in a comparison, outer space, so when we measure the temperature of space, we have approximately 2.7 Kelvin in outer space. So LHC is much colder than outer space. The whole cool down needs approximately 1 month, and each dipole magnet, which is 50 meters long, shrinks several centimeters during that, which also has to be taken into account because otherwise pipes would break. The cryogenic system is that we have at each of the 8 points at LHC, we have compressors to cool down the liquid helium or the helium itself. And then we compress the helium and pump it down. We have one gaseous helium stream, which is at 15 Kelvin, and we have one liquid helium stream at approximately 4.5 Kelvin. And then we pump it underground. And then we have something called cold compression system. And the cold compression system even further reduces the pressure of the helium, that we have in the end a helium which is at 1.8 Kelvin, so it can really cool down the magnet itself. And helium has a very interesting effect because at 2.1 Kelvin it becomes something called superfluid, so it basically can win around like holes, for example, or walls. It can basically flow against gravity, which is quite interesting. And it has also a very high thermal conductivity, and that's also why we use superfluid helium here. And that's why we cool down the whole magnets that low. And one other interesting effect is also that the LHC tilt angel, which is 1.4%, has to be taken into account because we have very low pressure inside all the tubes or all the system. So it's at 60 millibars, but we have sometimes to pump the helium against gravity or going down. So we also have to take into account the LHC tilt angel to not have wrong pressure levels at the whole LHC itself. Okay.
All right, so you probably already got the idea that, that what we've done in the last 20 minutes was only solve the first of the 3 challenges we had, which was actually bending the beam around a circular trajectory. So I'm trying to go to the other challenges we have lined up in the beginning. And the first one of that is the actual acceleration of the particle beam. And as large synchrotrons, for example, like the LHC, they use radio frequency or RF systems to do this acceleration. And I'm just going to go do a quick recap of the LHC beam and RF and how they interact. So Severin mentioned already that the particles in LHC actually come in bunches, so in packets that contain about 100 billion protons. And those bunches are spaced when they are running around the LHC approximately 25 nanoseconds apart. And starting from that, the tasks of the RF system are basically twofold. It first has to ensure that these bunches are kept tightly together in a process that we call longitudinal focusing. And the second task is to care for the actual acceleration of the particle bunches. So from their injection energy, when they come from one of the pre-accelerators, up to their final energy that they are supposed to collide at during the physics run. So in general, you can imagine RF as being a quickly alternating electric and magnetic field components. And in the LHC, this RF energy is basically injected into what is called a cavity, which is a resonant structure. And there the particle beams traverse through while the field quickly alternates. And the RF signal or the energy basically interacts with the particle beam. So perhaps you know that the protons are positively charged, and then a negative polarity of the field would attract these protons, while a positive field location would basically move them away. And this has, after just injecting and with the frequency of this RF field being the same as the speed that the particles actually go around the LHC, solves the first of the 2 problems, which was the focusing, because actually the particles that are too slow arrive only when the field has already changed to the opposite polarity and actually get accelerated a bit, while the particles that are too fast, they are actually being decelerated a bit, and this is a process that we call the longitudinal focusing, which makes sure that the bunches stay neatly packed together. And of course, this would be relatively inefficient if we would only change the polarity of this field once for each of the proton bunches that pass by, which is why we do it 10 times. So we change the polarity, basically changes 10 times, or the frequency is 10 times higher than the bunch crossing frequency. And by doing that, we make sure that the change of this field is much faster, and therefore the particle bunches are packed much closer together, and the focusing is better. So here you can see these cavities that were shown in the previous picture as a schematic, how they are actually placed in the tunnel. So 8 of these huge cavities are used per beam, and they are the actual thing that is used to couple the RF energy into the beam and transfer it to the particles. They are also operating superconductively, so at cryogenic temperatures, to reduce the thermal stress and the losses that would otherwise occur in their materials. And these are actually, even though they are so big, similar to the magnets that had to be very precisely manufactured, these also have very small manufacturing tolerances and have to be precisely tuned to the RF frequency that is used to inject. So, and the second part of this that actually produces this high power RF signal, for that is used what we call klystrons. So klystrons are basically RF amplifiers. They are built from high power RF vacuum tubes. And they amplify this 400 megahertz signal that is used to transfer energy to the particles. And each of those klystrons produces about 300 kilowatts of power, and you can probably imagine how much that power for an individual unit that is, if you know that your microwave oven has like 2 or 3 kilowatts. And of course, as we have 8 cavities per beam, and 1 klystron always feeds 1 cavity, we in total have 16 of those klystrons, and they are in principle able to deliver a total energy of 4.8 megawatts into the LHC beam to accelerate it. But if we take a small step back, for now we have only solved the first of the 2 problems, which was to keep the bunches neatly focused, because currently the particles have been injected and the frequency is at some specific frequency, and actually they are only running basically in sync, the 2. So what we do after all the particle bunches from the pre-accelerators have been injected into LHC is that we ever so slightly increase the frequency, which of course also means that the particles need to accelerate together with the RF signal. And this is the mechanism that we use to accelerate them actually. And the change that is required to do this is very tiny actually. So it is less than 0.001% sometimes. That is used to change the frequency to actually make them go so much faster. So from their relatively low injection energy up to the top energy plateau that they need to have to produce the actual physics collisions. And an interesting question to ask here is, where does this signal actually comes from? If it needs to be so precisely tuned to some specific frequency, who generates it or who controls it? And that opens up the whole complex of the timing of the LHC of the machine. So actually this first signal that I mentioned, this RF signal, it originates in a Faraday cage, so in a specially shielded area somewhere on the Brevson side of CERN. And from there it is distributed to the low-level RF subsystem with the klystrons and the cavities. But inside this room there are also a number of other signals generated. The first one of that being this bunch crossing clock, which is the actual clock that signals 1 pulse basically every time, or changes polarity 1 time a proton bunch moves across a specific location inside the LHC. And another one is the so-called orbit clock, which always indicates the start of the first, or when one proton bunch has basically re-arrived at the same position and has completed 1 orbit. And you may ask the question why this is an important piece of information. But if you think back to this image that Severin has already shown about the accelerator complex, the big challenge that all this brings is also the whole synchronization of all these machines. Because you have to imagine that while these proton bunches run around the LHC and new ones are supposed to be injected from the outside, from another pre-accelerator, this has to be very precisely synchronized. So all these pre-accelerator systems actually share a common synchronized timing system that allows them to precisely inject a new packet of bunches at the right position, at the right location into the LHC. And this is a bit how such a timing distribution system looks like. It is only a very small excerpt of what it looks like, but it gives you an idea that somewhere underground in the LHC there's rooms full of equipment that is just used to distribute timing signals between different parts of the accelerator. And of course, as CERN is forward-thinking and realized that future colliders will need quite a bit more of all this synchronization, and that the requirements for how precisely everything needs to be synchronized is ever growing, they actually developed their own timing distribution standard, which is also openly available and available for everybody to use. So if you're interested, look that up. But of course, not only the the accelerator itself is interested in this information about what particles are where and how quickly they interact or how quickly they go around, but also all the experiments need this information, because in the end, they want to know, okay, has a collision occurred at some specific time in my experiment? And actually providing this timing information about when bunches have crossed their experiment locations is also vital for them to really time tag all their collision data and basically track which bunches were responsible for what kind of event or what event throughout their whole signal storage and processing chain, let's say. Good, so that is basically challenge 2 out of the way. So that was the acceleration of the actual particles and all the associated issues with timing. And the third issue we mentioned was that the particles need to, let's say, be kept from colliding with anything but themselves or the other beam. And that is why we need vacuum systems for. So again, it is not as simple as just putting a vacuum somewhere. Of course not. Because in fact, there is not only one vacuum system at LHC, but there are 3. So the first 2 of those are perhaps a bit less interesting to most of us. They are mainly insulation vacuum systems that are used for the cryogenic magnets. So they isolate, basically thermally isolate the magnets at those very cool temperatures from the surrounding air to avoid them getting more heat load than they need to. And there is an insulation vacuum also for the helium distribution lines that are actually distributing, delivering the helium to these magnets. And then the third one, which is perhaps the most interesting one, is the beam vacuum. So the one where actually the beam circulates inside the LHC. And this is a cross-section of what this beam vacuum typically looks like. So it is approximately this size, so very handful, let's say. And the question you may ask, okay, if I want to keep all the particles in my particle beam from colliding with anything they're not supposed to, for example, rest molecules of remaining air there, how many molecules can there still be? So somebody has to make up that number. And typically you express this as a quantity called the beam lifetime, which basically says if you were only to keep those particles circulating in the accelerator, how long would it take until they have all dispersed and lost their energy due to colliding with rest gas molecules. And it was decided that this should be at a value of 100 hours, is what the beam should basically be able to circulate without collisions, without being lost. And this gave the requirement for pressures down to about 100 femtobar, which is a very small, very, very tiny fraction of the atmospheric pressure we have here, which is about 1 bar. And to actually get to this level of vacuum, it requires multiple stages and multiple components to actually get there. So the initial vacuum inside these beam tubes, which are basically going throughout the whole LHC tunnel, has the volume of approximately the Notre Dame Cathedral. So the first step of getting all the air out of these beam tubes is using turbomolecular pumps. And then there needs to be more mechanisms to reduce the pressure even further, because these pumps are not able to reduce the pressure to the levels required. And they actually use a relatively clever trick to do that, which is the use of cryopumping. I cannot show that. Okay, so the outer wall of this beam pipe cross-section that you see here is actually also where the very cold helium inside the magnets is outside of. And what that does is it leads to an effect called cryopumping. So actually any rest gas molecule that hits this wall actually condenses there. And as the molecules condense there, they are of course removed from the atmosphere inside this beam pipe, which removes them from the atmosphere and increases the quality of the vacuum. And with the use of this, and in the warm sections, the use of getter coatings, which are basically able to trap gas molecules, you are able to reach the crazy vacuum levels that are required to make this happen. But They realized also during the design that one big problem for the first time in an accelerator, another effect will create a significant problem for the vacuum, which is the generation of synchrotron radiation. So synchrotron radiation is a byproduct of when you do bend a particle beam. It results in a phenomenon called synchrotron radiation. And when this synchrotron radiation, as it goes straight on and is not bent, hits the walls of this vacuum system, or in this case of the beam pipe, it actually liberates molecules from there and reintroduces them into the vacuum, which of course then makes the vacuum worse again. An additional problem that gives the synchrotron radiation is that it also gives a significant heat load. And if you need to dissipate all this heat that is generated through the very cold helium, this is not a very efficient process, because making this helium so cool is actually a very energy-intensive process. And just removing a single watt of thermal power through this superfluid helium costs about 1 kilowatt of energy. So that is not the most efficient part. And this is why the cross-section you have just seen includes another large component, which also technically belongs to the vacuum system, which is called the beam screen. And this beam screen is basically another tube running inside the beam pipe, of which we have, of course, two, which runs inside the magnet cold bores. And it shields the synchrotron radiation heat load from the outer walls, which are at 1.8 Kelvin, while this pipe itself is actively cold to only about 20 Kelvin of temperature, which is much more efficient to dissipate this heat. So it is basically a steel tube about 1 millimeter thick. It has these pumping holes where like hydrogen gas molecules can go out of. On the inside, it has a copper coating, which is used to reduce its electrical resistance, which is required because the beam, while it circulates, also induces current that would otherwise flow inside this tube, which is really, and if you think about it, only a simple tube, and it would increase the heat load again. So a lot of engineering already has to go into a very simple piece of thing like that. After having spoken so much about all the things required to just make a beam circulate and accelerate and so on, now it's probably also time to talk a little bit about the beam itself and how to control it and how to instrument, how to measure things about this beam, even without going yet about collisions and doing actual physics experiments. So the first important bit that is able to basically control or influence the beam here is what's called the beam cleaning or collimation system. So typically such a particle beam is not very clean. It always travels associated with what is called halo of particles around this core area that is less than a millimeter wide, where most of the intensity is focused. And these particles outside we want to remove because they otherwise would be lost inside the magnets and, for example, would lead to quenches of the superconducting magnets. And for collimation, we basically use small slits that are adjustable and are located at two main locations of the LHC. So they have collimation systems there with vertical and horizontal slits that can be adjusted in width in order to scrape off all the particles that they do want to get rid of and extract out of the beam, while only the core part can circulate and produce clean collisions without any background that otherwise would need to be accounted for. And then there's a whole other open topic of beam instrumentation. So when you run a particle accelerator, you want to measure various quantities and performance figures of such a beam. And it is crucial for correct operation and for the highest performance, getting the highest performance from an accelerator. And there are a lot of different types of those, and I want to go quickly over why we have them and what we do with them. So the first and most basic measurement you want to do is the beam current measurement. So the beam current is a basic accelerator beam intensity measurement. So it gives you an idea of how strong the beam that is running inside your accelerator is, and it is measured using these DCCTs, or DC current transformers. And their basic principle of operation is that while the particles move through this torus, which is actually a coil or a transformer, it uses a voltage there that you can measure and then use to quantify the intensity of this beam. And the big challenge here is that the dynamic range this instrument needs to capture is really large, because it has to operate from the lowest intensity pilot injection beams up to the full energy, full number of bunches running inside the LHC. So it has to cover 6 orders of magnitude of measurement dynamic range. Then the second thing when talking about collisions is the luminosity measurement. So luminosity is a quantity basically said to measure the rate of interaction of the particle beams. So to give you an idea of how often interactions happen inside the experiments or where you want them to happen. And this measurement is used to, first of all, adjust this interaction rate to a target value, which is optimal for the experiments to function, and to equalize the interaction rates in different experiments. So different experiments also are specified to have the same interaction rate, so they can get the same, let's say, statistical quality of their data. So it's used to equalize those. And then as a third thing, this system is also used to measure the crossing angle of the beams. So as you may know, at some points when the beams are collided, they collide at an angle that is very small. And this angle is actually measured also very precisely in order to adjust it correctly. And it is measured to less than a thousandth of a degree, which is, again, a very impressive feat, given that the detection principle of this measurement is only measurement of some neutral particles that are a result of the particle interaction of the beam, of the collision. Okay, so that is number 2. Then number 3 that we have is the beam position monitor, because along the LHC, you also always want to know where the beam is at any given time. So you want to measure the position of the beam inside the beam pipe in order to optimally adjust it to the position you want to have it. And for that, we use these beam position monitors, of which we have more than 1,000 installed along the LHC. So they are typically capacitive probes or electromagnetic strip lines, as you can see on top and bottom respectively. And they basically are distributed along the LHC and provide position of the particle beam along the accelerator, which can then be used to tune, for example, the magnets. All right, then we have beam profile. So after the position, that gives you an idea where the beam is. You also want to know its intensity distribution. Basically, when you would do a cut through the beam pipe somewhere, you want to know how the intensity profile looks like. And for that, we have basically 2 measurement systems. One measures the profile in X and Y directions. So if you really would do a cut, and it gives you something like this. And it's, for example, done with wire scanners, which is literal, very thin wire that is moved through the beam. And then the current that the beam moving through this wire generates is used to generate such a profile map when scanning with this wire. And the other one is the longitudinal profile, which gives you an idea about the quality of your RF system. And there you want to know how the intensity profile of your beam looks like if you were looking only at one spot of the accelerator and the beam would pass by, and you would basically see over time how the intensity looks like. And then as the last bit of beam instrumentation, there's the beam loss monitors. So they are these yellow tubes that are located on the outside of mostly all the magnets, of the dipole and quadrupole magnets and so on. Again, there's more than 1,000 of those. And the idea here is that you need a lot of detectors that are basically small ionization chambers, which detect any showers of secondary particles that are generated when one of the high energy protons are lost somewhere in the magnet materials. So these are really used for protection of the system, because if a specific threshold of energy losses is detected, then the accelerator needs to be quickly shut down, which is why they have to react in a matter of nanoseconds in order to keep the accelerator safe, because any interaction of the particle beam with, for example, the magnets could just destroy huge amounts of money and of time that wouldn't be need to rebuild. And as a last and final thing, we have spoken 1 or 2 times already about shutting down the LHC, which sounds also trivial at first, but really is not. So the last thing here is what we call the beam dump. So the energy content that is contained in those particle beams, it could be used if it were shot on a copper target. It could just melt 1,000 kilograms or 1 ton of copper instantly. So during beam extraction, so the process of getting the particle beam out of the LHC, this energy needs to be dissipated somehow. And for that, this special beam dump area is constructed. So there are fast kicker magnets that are used to that are able to ramp up in a really, really short amount of time, of microseconds. And then the beam is carefully and in a controlled manner directed into a set of concrete blocks that is basically big enough to dissipate all this energy when required. And in the process of doing so, it also heats up to about 800 degrees Celsius, and then, of course, also needs the associated time to cool down again. Good. So as you may or may not know, currently the LHC is not in operation. So LHC currently is undergoing its second long shutdown phase, or LS2. But what we do when the LHC is in operation is that we have these status dashboards that you can see here that are distributed all around CERN and can be used by anyone, any passerby, to basically monitor what the current operation mode or the current situation of the accelerator is, and can be used also to quickly see if like an operator needs to go somewhere or is needed, or how the shift planning for the next shift works out, and so on. And on the right side, you would see what this currently looks like. So basically, black screen saying next beam expected in spring 2021. And the good thing about these status pages is that you can actually see them from your home, because they are also openly available as most of the stuff we do at CERN. So if you are interested, then perhaps in a year from now, or a bit longer than a year, it would be quite interesting to follow all the commissioning process of when they are trying to start the LHC back up, and follow that process from your home. Otherwise, if you now feel the urge to maybe visit CERN, pay some of the things we talked about a visit, or are just generally interested, CERN offers a variety of tours free of charge. So if you're interested in that, visit that website, and we would be happy to welcome you there. And with that, thank you very much for your attention.
Thank you, Stefan and Severin. If you have questions, there are 6 microphones in the room. Please make a queue, and we start with a Signal Angel. Signal Angel, please, yes. First question.
There is said to be a master red button for shutting down the whole system in case of heavy problems. How often did you push it yet?
Master red button?
The master button.
Like a shutdown button.
To answer, I can not really understand you. I think the question was about how often basically we use the beam dump system to basically get rid of the beam. Is it correct?
I guess so.
Yes,
I guess so.
I think there's a master button.
There is not only one master button. There are several master buttons. These are switches. It calls beam interlock switch. Basically, at every operator's screen, there is basically one beam interlock switch. I don't know. I think sometimes they get rid of the beam just because, I mean, when we have LHC at full operation, Stefan talked about the luminosity. So what is happening that in the beginning we have a very high amount of luminosity, so many particles collide on each other. But over time, like after 12 or 15 hours or whatever, basically luminosity, so the amount of particles which collide with each other is going down and down, so the luminosity decreases. And then at some point in time, basically the operators decide that they will now get rid of the actual beam, which is inside LHC, and basically will recover the whole machine and then restart the machine again. And this is done sometimes, I don't know, every 12 hours, sometimes after 24 hours, something like that, yes.
Cool. And microphone number 4, I think.
Yes. So where's the energy coming from? So do you have your own power plant or so?
No, not really. Not really. Basically, we get all the power from the French grid. So we have relatively big power trails coming from the French grid. So we get 450 kilovolts of power there. So basically, the voltage is quite high. Then we have our own transformers on site. And I think only a little bit smaller fraction of the energy is coming from the Swiss grid. So basically, we use most of the energy it's coming from the French grid.
Okay, thank you.
Thank you for your question. And microphone number 1, please.
Hi, thank you for your presentation. If I'm not wrong, you said the beam can warm a block of concrete to 800 Celsius. Would it be possible to use it as a weapon?
Very likely not, and CERN very much condemns these actions in any form, I guess. So CERN operates in a purely peaceful mission, and they would never think about using their particle beams as a weapon. And even if they could, it is probably not the most practical thing to do, I guess.
But if your telephone is again hanging up, you can destroy it, right? And microphone number 6, I think.
Yes, so you said you can stop in nanoseconds, but just the light would go just 50, let's say 30 centimeters in a nanosecond. How will you be able to scale in this small time?
No. So what I was talking about is that these magnets that are used to extract the beam out of the LHC they have reaction times or ramp up times that are in the order of 1 to 3 microseconds. So not nanoseconds, but microseconds. And really only then, basically, the particles still circulate, in worst case, one full turn, and are only then moving outside of the accelerator. Yeah.
And microphone number 1 again.
So do you have any photos of the front of the dump block? It has to look like it's got hit a lot.
No, not really. I think that's one of the only pictures we could find about the beam dump system. And this area is, I think, it's not really opened anymore. So since operation of LHC, which was basically LHC started in 2008, and since then the beam dump system was not opened again because it's completely sealed in stainless steel, and that's why it was not opened anymore.
Cool. Question from the interwebs.
Regarding power supply, how do you switch or fine control the currents? Are you using classic silicone transistors, off-the-shelf IGBTs?
Yes. Yes. The system was developed at CERN, and I think that's quite common at CERN, that we basically develop all the technology at CERN, or try to develop nearly everything at CERN. But then production, for example, is put into industry. And yes, these are relatively classical power converters. The interesting or challenging part about the power converters is really that the current has to be measured quite precisely and also controlled quite precisely. So there we use also DCCTs, what Stefan mentioned before. But basically all this control mechanism there, that's one of the big challenges there.
Cool. Microphone number 1 again.
Yeah, you talked about the orbit clock that detects when the bunch is completed one round. How is it possible to detect which is the first bunch?
Yeah, so it is actually not detected, but this clock is actually something that is constructed. So basically what we do is we count these cycles of the RF cycle. Maybe I can open that slide. So somewhere there is a counter that basically knows how many 40 megahertz clock cycles a full rotation takes, and then at some point decides this is number 1, and that's also where they start counting when they inject bunches into the LHC. So there's no marker, let's say. But there is a certain structure to the beam, so you could potentially do that. So for example, for these longer periods where the kicker magnets need to ramp up, they have something they call the abort gap, so a number of bunches that are never filled, but are always kept empty, so the magnets have enough time to deflect the beam when the next bunch comes around. So you could probably measure that, but it's much easier to do it the other way around.
Microphone number 4, please.
You said you had quite tight needs for the timing clock. Is it tight enough that speed of light was a limit with the distances between locations, or that was not a concern?
No, it is a concern. So because just distributing a cable for 27 kilometers produces just considerable run times of electrical signals. All the delays or all the cables need to be measured precisely for their delay and then calibrated out. So all the experiments get their clocks at the right time shifted, compensated for the light time, let's say, that it just takes to get the signal there. Yeah.
And again, the interwebs.
Is it dangerous to stand near the concrete cooling blocks? Like radioactive-wise, or I don't know.
Yes. Yeah.
Not recommended.
Not recommended. We have a very good interlock system. Also, all the doors have switches. So basically, when one door is basically opened, then basically the whole machine will be shut down. So we have a very critical and safety-related access system at LHC. Yeah. Maybe you watch Angel and Demons, this Hollywood movie. There we have the eye scanners are shown. It's a little bit, it's Hollywood, but there we have eye scanners, so iris scanners. So every time we want to go to the tunnel, for example, then we have to let also our iris be scanned, because otherwise we will not be able to go to the tunnel. So there's a very sophisticated access system to really go to the tunnel. So when there is operation, the whole tunnel access is completely blocked.
Cool. Microphone number 1, please.
What is the exact question? The exact reason to have each experiment every side? So far apart on the LHC. On opposite sides.
Basically, you are talking about Atlas and CMS. The reason for that is because when these two experiments were constructed, there was a little bit the fear that particles which are not strapped away can basically interact with at the two experiments, so that they really are like the most fast away, like they have a very big distance from each other, so there's no interaction between them. That's why we basically put them at 0.1 and 0.5.
Yeah.
That's the reason why.
If I can see it correctly, microphone number 5.
Yes, hello. Yeah. I've seen that you've also using the CAN bus. What are you using the CAN bus for in CERN?
I know of at least one use, but that is inside an experiment. So there are, as far as I know, investigations on the way to use CAN bus to do the actual control of the detectors of one experiment. I don't know if there's a use inside the accelerator itself, so apart from the experiments. But perhaps if you come by afterwards, we can find one.
Thank you.
Microphone number 1.
Do you have any official data about how many tons of duct tape are used in daily operations?
No.
What about zip ties?
Many, yeah, millions, billions.
Okay, as far as I can see, the interwebs again with a question.
Yes. Do you know your monthly power bill?
No, not really.
No,
sorry.
No, but it is, I think, a fact that the contribution of France, which is the main contributor in terms of energy, that it is part of their contribution to contribute the electricity bill, basically, instead of paying money to CERN. That's as far as I know.
Yes, and also we shut down LHC and the accelerator complex during like the winter time. And one of the reasons for that is because electricity is more expensive during winter time in France than in summer.
In this case, I can't see any other questions. I have a maybe stupid question. You said earlier you have to focus and defocus the beam, but as we know, you accelerated already the particles. Why do we have to focus the beam?
Because every time when we also like have dipole magnets, then basically we bend the particles around an arc. But then they are also defocused a little bit, and also the Coulomb force is there a problem because we have equally charged particles in the bunch or in the whole beam itself, so they will by themselves will basically go out of each other, and if we would not focus it again, then basically we would lose the whole beam in the end.
Thank you. I don't see any questions. Internet? In this case, thank you very, very much, Stefan and Severin. Please, with a warm applause. The Large Hadron Infrastructure Talk.